NASA, meanwhile, has successfully averted a big problem. Its engineers had sent a wrong signal to Voyager 2 and had lost contact for nearly about 10 days.
Engineers sent a wrong signal to Voyager 2, and now the space probe is on its own at a distance of 20 billion kilometers.
Voyager 2, which was launched by NASA in 1977, is among the most amazing space exploration accomplishments in human history. The spaceship is still sending data as it moves over the wide reaches of space more than 40 years after it was launched. What has it seen during the last 40 years? Because Voyager 2 has no intention of ceasing to satiate human curiosity, the human search for knowledge and desire for more about the solar system and the universe continues. We're heading to the edge of the solar system, so fasten your seatbelts. Crossing the Heliopause, to put it simply, let's discuss the heliopause. The heliosphere, the bubble that the sun forms around itself, is made up of charged particles known as the solar wind. The interstellar medium, which is made up of particles from stars and other astronomical sources, is where these particles eventually meet particles from outside the solar system after traveling deep into space. The heliopause is the point at which the solar wind is no longer powerful enough to push against the interstellar medium. It resembles the edge of the sun's bubble. In November 2018, Voyager 2 crossed the heliopause for the second time, after its twin, Voyager 1. The heliopause is the line where the interstellar medium, or substance that fills the space between stars, and the solar wind, or charged particles released by the sun, meet. Voyager 2 saw a dramatic decrease in solar wind particle density and an increase in interstellar particle density when it passed this limit. This verified that the spacecraft had left the heliosphere, the bubble-like area where the sun's effect is most noticeable. Measurements of plasma density. When Voyager 2 passed through the heliopause, one of its unique instruments was still operational. The electrically charged gas in space, known as plasma, was measured. In contrast to the plasma inside the heliosphere, Voyager 2 discovered that the plasma in interstellar space was denser. Because it gave scientists a better understanding of the environment outside the sun's influence, this was a significant finding. Because Voyager 2's plasma instrument was operational when it reached the heliopause, scientists were able to obtain direct measurements of plasma density, unlike Voyager 1. The interstellar medium is denser than the solar wind, as evidenced by the notable rise in plasma density observed by Voyager 2. Our knowledge of the transition zone and the relationship between the heliosphere and interstellar space has improved as a result of this data. Observations of magnetic fields. High-energy particles known as cosmic rays are produced when stars explode and other significant galactic events take place. The sun's solar wind serves as a shield inside the heliosphere, limiting the quantity of cosmic rays that can reach us. Voyager 2 discovered much more cosmic rays after it passed over the heliopause, demonstrating how the heliosphere shields everything within it, including Earth. The magnetic field near the solar system's boundary was also measured by Voyager 2's equipment. It's interesting to note that the spacecraft saw that the interstellar magnetic field's direction resembled that of the sun's, indicating some degree of connection between the two. This discovery opened up new scientific possibilities by casting doubt on some preconceived notions about the boundaries of interstellar space and the end of the sun's influence. Energetic particles and cosmic rays. Voyager 2 saw a significant shift in the behavior of cosmic rays, which are high-energy particles that come from outside the solar system, as it moved into interstellar space. The solar wind partially protects the solar system from cosmic rays inside the heliosphere, but Voyager 2 experienced a greater intensity of these particles outside the heliopause. This reaffirmed the heliosphere's function as a shield against cosmic radiation. The dynamic nature of the boundary. The heliopause is a dynamic and changeable zone rather than a static limit, as demonstrated by Voyager 2's observations. The breathing effect is caused by the heliosphere's expansion and contraction in reaction to solar activity. These results imply that the boundary is far from uniform and highlight the intricacy of the sun's interaction with the interstellar environment. An interstellar space window. Voyager 2 moved into interstellar space after passing through the heliopause and started examining the characteristics of the interstellar medium. In contrast to the solar wind's hot, low-density plasma, it found a chilly, dense plasma environment. These measurements give a unique window into the characteristics of the interstellar medium, revealing hints regarding the galaxy's genesis and development. For us, what does this mean? The voyage of Voyager 2 aids in our comprehension of the Sun's protective bubble and its interactions with the surrounding environment. This information helps scientists understand the universe outside of our solar system and is crucial for upcoming space missions. It's similar to locating the galaxy's neighborhood boundary and getting a glimpse of the cosmos beyond. The moment of crossing the Heliopause was momentous. It demonstrated that Voyager 2 had formally entered interstellar space and exited the solar system. Despite being billions of kilometers away from Earth, Voyager 2 is still sending back useful data that helps us learn more about the interstellar medium. When Voyager 2 crosses the Heliopause, it's like entering a new world and arriving at the solar system's edge. Its findings regarding interstellar space, cosmic rays, and the solar wind have altered our understanding of our role in the cosmos. Launched decades ago, this small spacecraft never ceases to amaze us with its amazing voyage into the unknown. Future exploration will be significantly impacted by the findings made by Voyager 2 at the solar system's edge. They offer a starting point for comprehending the interstellar medium and how stars, like our Sun, interact with it. Future missions like the Interstellar Probe, which intends to carry on Voyager's legacy by venturing farther into interstellar space, will be developed using these discoveries as a guide. Two pioneering spacecraft scientists have been able to better comprehend the boundaries of the solar system by comparing the data from Voyager 1 and Voyager 2. For example, the uneven form of the heliosphere was highlighted by the slightly different conditions that both spacecraft encountered when they crossed the Heliopause. These variations imply that external elements, such as the local interstellar magnetic field and pressure, have an impact on the heliosphere. NASA launched Voyager 1 and Voyager 2 in 1977 with the goal of studying the outer planets and beyond. These spacecraft are considered to be among the most remarkable accomplishments in space exploration. We will discuss the similarities and differences between Voyager 1 and Voyager 2, emphasizing their complementary roles in advancing humanity's understanding of the solar system and interstellar space. Despite having nearly identical designs and similar missions, the two spacecraft traveled different paths and made unique discoveries along the way. NASA's ambitious Voyager mission included the 1977 launches of Voyager 1 and Voyager 2. Voyager 1 launched on September 5 after Voyager 2 launched on August 20. Voyager 1 reached its planetary objectives before Voyager 2 because it was launched later but was put on a quicker trajectory. In order to explore several planets using gravitational slingshots, both spacecraft were built to capitalize on a rare alignment of the outer planets that happens about every 176 years. Jupiter and Saturn were the primary targets of Voyager 1, which produced groundbreaking information and pictures of these gas giants and their moons. The comprehensive study of Jupiter's Great Red Spot and the active volcanoes on its moon Io, the first proof of volcanic activity outside of Earth, was one of its most well-known findings. Voyager 1 investigated Saturn's complex ring system and Titan, its largest moon, whose thick atmosphere was of significant scientific interest. Voyager 2, the only spacecraft to date to examine these ice giants up close, had a more extensive planetary mission that included visits to Uranus and Neptune in addition to Jupiter and Saturn. 10 new moons were found by Voyager 2, which also revealed Uranus' skewed magnetic field. It discovered the solar system's fastest winds at Neptune and took breathtaking pictures of the planet's deep blue atmosphere. In order to investigate the interstellar medium, Voyager 1 was steered higher and out of the solar system's plane after completing its flybys of Jupiter and Saturn. On the other hand, Voyager 2 proceeded to investigate Uranus and Neptune by continuing its journey through the solar system's plane. The two spacecraft were able to offer complementary viewpoints on the outer solar system and beyond because of their divergent paths. Eventually, both spacecraft passed through the Heliopause, which is the line separating interstellar space from the Sun's influence. In August 2012, Voyager 1 became the first artificial object to enter interstellar space after successfully navigating through the Heliopause. Its departure from the heliosphere was confirmed when it noticed a sharp decrease in solar wind particles and an increase in cosmic rays. November 2018 saw the launch of Voyager 2. In contrast to Voyager 1, Voyager 2 was able to detect plasma density directly since its plasma instrument was still operational at the time. Scientists were able to learn more specific details regarding the change from the solar wind to the interstellar medium because to this, the same set of instruments, including its cameras, magnetometers, and plasma detectors, are carried by both Voyager spacecraft. But with time, these instruments' modes of operation changed. In order to save energy for its other instruments, Voyager 1's cameras were switched off following its planetary mission. Consequently, it was unable to take pictures of its interplanetary flight. Since Voyager 1 was unable to measure the density and temperature of interstellar plasma directly, Voyager 2, with its plasma instrument in operation during its Heliopause crossing, supplied vital information. The golden records, which are phonograph records with sounds and pictures that symbolize the variety of life and culture on Earth, are carried by both spacecraft. In order to communicate with any extraterrestrial species that could come into contact with the spacecraft, these records were created as a kind of time capsule. Despite being identical, both records represent humanity's curiosity and hope for connections outside of our solar system. Our knowledge of the solar system and interstellar space has been revolutionized by Voyager 1 and Voyager 2 taken together. From the structure of the heliosphere to the dynamics of planetary atmospheres, their data has helped scientists make many discoveries. As they continue to function well beyond their anticipated lifespans, they also represent human ingenuity and the spirit of exploration. Although they have traveled distinct routes, the twin spacecraft Voyager 1 and Voyager 2 are both dedicated to exploring the universe. Voyager 2's extended planetary mission and operational plasma instrument have offered unique insights into the outer planets and the border between the solar system and interstellar space, even though Voyager 1 was the first spacecraft to traverse interstellar space. Collectively, they have given humanity a better knowledge of our position in the cosmos and motivated countless generations of scientists and adventurers to keep aiming for the stars. The pressure on Voyager 2 for more than 40 years, Voyager 2 has been exploring the universe and providing groundbreaking information about the solar system and beyond. Voyager 2 continues to transmit important data from billions of kilometers distant, even after its historic planetary encounters and entry into interstellar space in 2018. Almost unthinkable, billions of miles. Scientists are optimistic about what Voyager 2 will uncover as it continues its journey into interstellar space, despite its age and distance. These are some of the main scientific objectives and expectations related to this amazing spacecraft. The mapping of interstellar space in detail comes first. Scientists are eager to study the characteristics of the interstellar medium, or the material that fills the vast space between stars, as Voyager 2 ventures farther into interstellar space. Voyager 2's instruments are especially suited to investigate the density, temperature, and composition of this medium, which is made up of interstellar dust, plasma, and cosmic rays. By comparing data from Voyager 2 with its twin, Voyager 1, researchers may develop a more detailed picture of the interstellar environment and how it interacts with the heliosphere. Experts seek to better comprehend the heliosphere's form and behavior. The heliosphere, the bubble-like zone formed by the sun's solar wind, protects the solar system from many cosmic rays and interstellar particles. The voyage of Voyager 2 offers a unique chance to investigate the behavior and evolution of the heliosphere. The shape of the heliosphere, which seems uneven based on Voyager 2's measurements, is of special interest to scientists. Models of the interactions between the heliosphere and the interstellar medium can be improved with the use of ongoing measurements of the solar wind and interstellar particles. The ability of Voyager 2 to monitor the interstellar magnetic field is one of its main accomplishments. Researchers anticipate that the spacecraft will yield additional information about the behavior of this magnetic field far from the Sun, understanding the larger galactic environment and how magnetic fields affect the motion of charged particles, such cosmic rays, throughout the galaxy depends on this knowledge. Voyager 2's mission places a lot of emphasis on cosmic rays, which are high-energy particles that come from supernovae and other astronomical occurrences. Because the spacecraft is in interstellar space, the sun's magnetic field cannot interfere with its ability to measure cosmic rays. Researchers want to know more about the origins of these particles, their motion through space, and how the heliosphere protects against them. This study may shed light on the dynamics of our galaxy and the life cycles of stars. Additionally, interstellar dust particles, remaining pieces of old stars that aid in the creation of new stars and planets, can be studied by Voyager 2. By examining these particles, scientists can acquire a deeper understanding of the building blocks of the galaxy. By providing hints about the processes that shape our universe, Voyager 2's observations can assist in addressing problems regarding the distribution, size, and composition of interstellar dust. Future interstellar mission planning continues to be informed by the data gathered by Voyager 2. Voyager 2's discoveries will be expanded upon by the Interstellar probe, a projected spacecraft that is intended to travel far further than Voyager. Voyager 2 establishes the foundation for new technologies and scientific goals in the exploration of deep space by conducting a more thorough examination of the interstellar medium and the heliosphere's edge. The potential for the unexpected to be revealed by Voyager 2's voyage is among its most thrilling features. Voyager 2 has consistently exceeded expectations, from finding active volcanoes on Jupiter's moon Io to identifying the unexpectedly high density of interstellar plasma. Scientists are nevertheless open to the prospect of new occurrences as it ventures farther into unexplored area, whether they have to do with particle behavior, cosmic architecture, or interstellar physics. Beyond its scientific goals, Voyager 2 offers important insights into engineering and the resilience of spacecraft in harsh conditions. With its power and instruments gradually declining, scientists are using Voyager 2 to test how long a spacecraft can operate and communicate in deep space. These lessons will undoubtedly inform the planning of upcoming missions that seek to conduct even more exploration. Voyager 2 has the potential to reach areas affected by the stellar winds and magnetic fields of other stars as it moves deeper into interstellar space. In order to gain understanding of how stars interact on a galactic scale, scientists believe that Voyager may eventually find evidence of these nearby influences. The voyage into interstellar space by Voyager 2 is far from over. The shape of the heliosphere, cosmic rays, the interstellar medium, and the secrets of the galactic environment are all topics of great interest to scientists. Despite its age and the immense distance from Earth, Voyager 2 continues to push the boundaries of human understanding, delivering a view into regions of space never before explored. Voyager 2 continues to be a monument to human ingenuity and curiosity as it explores the unknown, encouraging subsequent generations to explore the cosmos even further. Voyager 2 helped us learn more and more about the final 3 planets in the solar system, which are the furthest from the Sun. It is the only spacecraft that has made close encounters with all 4 of the gas and ice giants, Neptune, Uranus, and Saturn. Despite not visiting Pluto, Voyager 2's findings at these far-off planets helped to shape our knowledge of the solar system by revealing important details about their atmospheres, moons, magnetic fields, and other features. In August 1981, Voyager 2 arrived at Saturn, expanding on the discoveries made by Voyager 1 before it. It revealed important details about Saturn's intricate moon, ring, and magnetic environment. By identifying spokes, gaps, and braided patterns inside Saturn's rings, Voyager 2 demonstrated their complex structure. These results implied dynamic processes, including particle clumping and dispersing and gravitational interactions with moons. The spacecraft's thorough observations of Saturn's atmosphere showed bands of clouds formed by strong jet streams and high winds surpassing 800 kilometers per hour. Enceladus, one of Saturn's moons that Voyager 2 spotted, showed signs of resurfacing processes, suggesting possible geological or possibly cryovolcanic activity. Later missions investigating the possibility of life on Enceladus were made possible by this discovery. It verified Saturn's powerful magnetic field and how it interacts with the planet's moons and rings to produce distinctive auroras. Let's move on to Uranus and see why it is known as the tilted ice giant. Voyager 2, which passed by Uranus in January 1986, is still the only spacecraft to have done so. Its findings showed Uranus to be an odd and enigmatic planet. Uranus' severe axial tilt of 98 degrees, which causes the planet to practically roll on its side as it orbits the Sun, was confirmed by Voyager 2. Because of its unusual orientation, it experiences harsh weather and seasons. A frigid, featureless atmosphere primarily made up of hydrogen, helium, and methane was found by the spacecraft. Uranus is pale blue-green because of the methane. Voyager 2 saw various weak weather patterns, such as faint banding and minor storm systems, despite its uninteresting look. Voyager 2 found that Uranus has a very uneven magnetic field that is inclined and offset from its center. Existing models were called into question by this peculiar magnetic pattern, which also implied a distinct interior structure. The complicated satellite and ring system of Uranus was highlighted by Voyager 2's discovery of 10 new moons and 2 more rings. Massive gorges and indications of previous geological activity were among the striking surface characteristics discovered during its investigations of moons like Miranda. The last time Voyager 2 visited a planet was during its flyby of Neptune in August 1989. It revealed fascinating insights into this faraway, active world. Voyager 2 discovered Neptune's stunning blue color, generated by methane in its atmosphere. Strong storms, such as the Great Dark Spot, a huge storm system the size of Earth, and some of the solar system's fastest winds, which may exceed 100 kilometers per hour, were found. Neptune's magnetic field was discovered to be slanted and offset from the planet's core, much like Uranus, indicating that ice giants share this trait. Voyager 2 discovered Neptune's feeble ring system, confirming the existence of arcs or clusters inside the rings that contradict the smoothness seen in Saturn's rings. The largest moon of Neptune, Triton, was photographed by the spacecraft, which showed active geysers spewing nitrogen gas. Triton may have been a captured object from the Kuiper Belt, providing hints about the outer regions of the solar system, based on its geological activity and retrograde orbit. Let's move on to a lost chance, exoplanet Pluto, removed from the list. Because flybys of the outer planets were prioritized on Voyager 2's trajectory, Pluto was not visited. Pluto was regarded as the 9th planet when the mission was planned, but not much was known about it. Pluto was revealed to be a complex planet with mountains, glaciers, and a thin atmosphere by the New Horizons mission in 2015, which would provide detailed images and data about the planet decades later. Despite not visiting Pluto, Voyager 2's findings of Triton offered a sneak peek at the icy, far-off objects in the Kuiper Belt, which includes Pluto. Voyager 2's observations of Saturn, Uranus, and Neptune revolutionized our knowledge of the outer solar system. It demonstrated the intricacy of magnetic fields, the variety of planetary atmospheres, and the dynamic character of moons and rings. The James Webb Space Telescope and planned missions to Uranus and Neptune, which seek to investigate these ice giants in greater detail, are examples of current and upcoming missions that are still guided by its results. By exploring Saturn, Uranus, and Neptune, Voyager 2 gave humanity a unique perspective on the outer solar system. The spacecraft revealed secrets that continue to motivate scientists and pique our interest in the universe, from Saturn's brilliant rings to Uranus' twisted enigma and Neptune's violent storms. Despite not going to Pluto, its findings set the stage for further research into frozen worlds near the solar system's periphery. By expanding our understanding of our location in the universe, Voyager 2 continues to stand as a testament to human inventiveness. Beyond expectations, picture the spacecraft that was constructed a few decades ago and is still in existence after 46 years. Voyager 2 is an example of both human brilliance and superior engineering. Designed to investigate the farthest planets of the solar system and beyond, Voyager 2 has long exceeded its initial mission constraints. It did. And it continues to relay crucial data from interstellar space more than 46 years after its launch. Voyager 2 was developed with durability and adaptability in mind, packed with cutting-edge equipment meant to resist the harsh environment of deep space. Built to tolerate severe conditions, Voyager 2 was meant to survive powerful radiation near Jupiter, the chilly emptiness of space, and the huge distances it would travel. Its sturdy frame safeguarded its scientific instruments throughout its journey. Voyager 2 produces power using a radioisotope thermoelectric generator, RTG. By converting heat from plutonium-238's natural decay into electrical power, this method enables the spaceship to function far from the sun, where solar panels would not be useful. Over billions of miles, the spaceship can communicate with Earth because to its high-gain antenna. Through NASA's Deep Space Network, Voyager 2 stays in touch even though its present distance causes signal delays of more than 18 hours. 10 scientific instruments, such as cameras, spectrometers, and plasma detectors, are aboard Voyager 2. The purpose of these equipment was to investigate the interstellar environment and the outer planet's atmospheres, magnetic fields, and moons. Redundancy was incorporated into several of Voyager 2's systems to guarantee that backups would be accessible in the event of a failure. This has been essential to keeping it operating for decades. One of Voyager 2's greatest accomplishments is its longevity, which far outstripped the 12-year mission period. Its long lifespan can be attributed to several factors. For more than 40 years, the RTG has been a reliable source of electricity, but its efficiency is progressively declining. By prioritizing power for critical systems and turning off non-essential components, NASA engineers have managed this decline. The components of the spacecraft were designed to endure prolonged exposure to the harsh conditions found in space. Despite decades of operation and the difficulties posed by deep space radiation and temperature extremes, its instruments and systems have remained reliable. As Voyager 2 ages, NASA engineers have come up with innovative ways to solve problems time and time again. For instance, they have remotely reprogrammed the spaceship to avoid malfunctioning parts, maximize power efficiency, and prolong its useful life. Engineers decreased wear and tear by using fewer moving parts, which has extended the lifespan of Voyager 2. Instead of using mechanical controls, many of its systems use electrical ones. Even though Voyager 2 was launched in the 1970s, software upgrades have enabled it to carry out activities that were not initially planned. It has remained relevant as new scientific issues have emerged because of its versatility. In actuality, though, it has existed for about 50 years. Even though Voyager 2 is billions of miles away from us, it nevertheless faces difficulties. Overcoming difficulties has been a hallmark of Voyager 2's lifespan. Operating a spacecraft billions of kilometers from Earth poses special hurdles. As the RTG's power production declines, engineers have prioritized powering just the most vital instruments and systems. This meticulous power management has allowed the mission to continue far longer than predicted. The growing distance makes communication slower and weaker. To stay in touch with Voyager 2, engineers have increased the sensitivity of Deep Space Network receivers located on Earth. Mechanical and electronic components degrade with time. NASA has depended on redundancy and innovation to cope for aged systems, including modifying software to bypass faulty components. Decades after its launch, Voyager 2 continues to bring back data about the interstellar medium, revealing insights into the space between stars that were impossible to get from within the heliosphere. The lifespan of the spacecraft has shown how important flexible and sturdy design are for space missions. Newer spacecraft like the James Webb Space Telescope and future interstellar explorers are using these lessons. The success of Voyager 2 has sparked plans for large-scale additional missions, such as investigation of outer planets like Uranus and Neptune and suggestions for specialized interstellar probes. Voyager 2 is a testament to human ingenuity and curiosity as it continues its journey into interstellar space. Its engineering prowess and the tenacity of the teams in charge are demonstrated by its capacity to function for decades under the most trying circumstances. Voyager 2's legacy will live on, encouraging future generations to push the limits of discovery even though its power supply will eventually run out. For more than 40 years, Voyager 2 has been able to surpass its initial mission objectives and continue exploring the unknown thanks to its incredible technical and technological capabilities. The inventiveness of its founders and the commitment of those who have overseen the mission throughout the years are responsible for its longevity. Voyager 2 continues to be a shining example of human accomplishment as it ventures farther into interstellar space, proving what is achievable when scientific aspirations and superior engineering are combined. The search for meaning in the cosmos. Voyager 2 poses important queries concerning the nature of the cosmos and our position in it as it ventures into the interstellar medium. What is outside the solar system's borders? Is there other intelligent life out there, or are we alone? Even while Voyager may not have the answers to these issues, its mission encourages us to look for them. Its investigation highlights our close ties to the cosmos and serves as a reminder that humans share many of the same elements as the stars. Voyager 2 challenges us to consider the significance of our place in the universe and the purpose of life by traveling so far from Earth. In addition to being a technological marvel, Voyager 2 is a powerful representation of human curiosity, inventiveness, and our quest for knowledge about the cosmos. Voyager 2 challenges us to reflect on our place in the universe, our common humanity, and the never-ending pursuit of knowledge as it travels into interstellar space and beyond the solar system's limits. Let's quickly examine Voyager 2's philosophical effects on humanity, emphasizing how it has influenced our outlook on life and motivated successive generations to consider possibilities beyond our planet's boundaries. Humanity is given a humble perspective on its place in the universe by Voyager 2's journey into interstellar space. The spacecraft's photographs of far-off planets, moons, and even Earth have highlighted how big space is and how little our world is in the overall scheme of things. By highlighting humanity's shared fate as occupants of a limited, fragile world, this viewpoint pushes us to think beyond national or cultural boundaries. Voyager 2 is a representation of humanity's unrelenting quest for knowledge. We had no idea what it would uncover when it was launched into space, but its findings have revolutionized our knowledge of the universe and the solar system. This readiness to explore the unfamiliar reflects a basic human quality, curiosity. The video ends, but Voyager 2 is not. It will reach new heights and uncover more solar system mysteries. See you at the following one.